Section 9.6, Colligative Properties that depend on the non-volatile solute concentration but not its nature. First, non-volatile solute means its vapor pressure is extremely low. And then you can see this colligative properties depend on the concentrations but not its nature. Let me give you an example. If you add 1 mole of sucrose in 1 liter of water, you will increase the boiling point of water while lowering its melting point. And you don't have to add sucrose. You can add 1 mole fructose. That's fine. You achieve the same effect. You can even add sodium chloride. Well, you just need 0.5 mole sodium chloride because it decomposes into 1 mole particles in water. So in the end, you have 0.5 mole of sodium plus and 0.5 mole of chlorine minus in water. It's still 1 mole of particles. It can be molecules, ions, or atoms in water. You can add magnesium chloride, but in this case, you just add 1/3 of a mole of magnesium chloride because in the end, you get 1 mole particles. So this is the so-called colligative properties. The boiling point elevation and the melting point depression of water depends only on the number of particles dissolved in water. It does not depend on its nature. However, I was exaggerating this sodium plus and chlorine minus. Well, they do affect the attraction and the repulsion in the mixture. So it's not really an ideal solution, but I'm just giving you a rough example to estimate the boiling point elevation and melting point depression. Alright, let's look at this mu-T diagram. This is chemical potential. This is the temperature at low temperature. The solid chemical potential is the lowest. And then when you increase the temperature from left to right, at the melting point, the solid chemical potential crosses the liquid chemical potential and the substance starts to melt. And then after that, we see this when temperature goes up. Now we follow along the liquid line. The liquid line has the lower chemical potential than the solid or the gas, so the liquid, until it reaches the boiling point. At this point, the liquid and gas lines cross right here. They have the same chemical potential. At a higher temperature, now you have just gas only because the gas line is lower than the liquid line or the solid line. Alright, so what if we add stuff into the liquid phase and make sure this substance can be dissolved in this liquid? If it doesn't dissolve, it doesn't help. If it's dissolved, it increases the entropy of water. And when you increase the entropy of water, you decrease the Gibbs energy of water and then the chemical potential of water. Remember the equation for G? G is H minus Ts, H is U plus PV, so G is U plus PV minus Ts. If you have a constant temperature, constant pressure, and then if you increase the entropy of the solution, you have a lower G. When you have a lower Gibbs energy, you have lower chemical potential at this temperature and pressure. When you have a lower chemical potential, we just shift this liquid line a bit lower and then see where does this new line, the solution line, crosses with the solid. Well, at a lower temperature. Where does this cross this gas line? At a higher temperature. This is why you observe the boiling point elevation and melting point depression at the same time. So basically, the liquid phase is stabilized by the solute, not because of the nature of the solute, not because of the attraction it feels from solute. It's simply because adding solute in water increases the entropy of water. But of course, I mean, if you add sodium chloride, there's probably going to be additional attraction between sodium plus and water and between chlorine minus and water. But actually that effect is in many cases not as significant as the entropic effect. So we're talking about the entropic effect right now. That's why this is a colligative property, because it does not depend on the nature of the solid. As long as it dissolves, you just need to count the number of particles dissolved in a fixed amount of water. So that's why you add 1 mole sucrose, 0.5 mole sodium chloride, or 1/3 mole of magnesium chloride. You achieve the same boiling point elevation and freezing point depression approximately.